going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about application of nanomaterials in catalysis, particularly photocatalysis and contaminant degradations and various CO2 conversions as well as liquid phase reactions that we will discuss. So, already we have discussed there are various type of metal oxide carbon based nanomaterials that we have prepared by considering different methods. So, today we will discuss the applications of nanomaterials, basically that may be gold or any other nanomaterial that is metal based or particles, and graphene oxides like that material. So, effect of that particle size means nanomaterials that is less than 100 nanometers. So, 1 to 100 nanometer within that range or any other range we can prepare by considering a particular method. So, then once we apply these nanomaterials for a specific reaction, so that play a crucial role in terms of catalytic conversions, reactant to product formations, product selectivity as well as yield of that product. So, that basically we will discuss. So, how this nanoparticles size effect different range of size, let us say 1 nanometers, 5 nanometers, 8 nanometers, different nanometers we can prepare, and how that affect overall performance of the reactions by considering few examples we will discuss. Also gold nanoparticle size effect for a specific reaction, so propene epoxidation reaction, so there we will discuss. Also graphene oxide, that is also carbon based nanomaterials that would be combines with the titania. So, then titania graphene or titania graphene oxides may form. So, that nanocomposite materials also would be discussed for a degradations of contaminants present in wastewaters. At the same time also by considering other nanomaterials we will discuss for CO2 conversions, that may be electrocatalytic conversions or photocatalytic conversions of CO2 into value added products. Okay. And some other metal based nanomaterials or metal oxide based nanomaterials that would be also prepared by a different method, that is core cells and nanoparticles that would be synthesized by considering one or two methods, and then applications of those core cell nanoparticles for a specific reactions for conversions at different functional groups or conversions of one particular compounds into another. So, how that materials each play different roles, that will be discussed. So, in heterogeneous catalysis, the chemical process that is particularly two different phase means gas and solid reactions, means reactant if it is gas, catalyst is solid, or maybe solid liquid reactions, reactant may be liquids and materials or catalysts that may be solids. So, that is called heterogeneous catalysis. This way reactants in presence of specific catalyst, that is nanomaterials or nanocatalyst, that would be converted into a desired product. Okay. So, this type of means heterogeneous catalysis means conversions of gas or liquid reactant into product. So, considering different nanomaterials, many industrial reactions are available and that is apply extensively. Okay. So, now the compositional and structural complexity of that nanomaterials in terms of particle size, shape, compositions, dopants, atomic clusters or metal support interactions. So, that significantly influence the catalytic performance in terms of adsorptions of the reactants, at the same time yield of the products. Okay. So, here so you can see one schematic is showing. So, here the growth of materials. So, the catalyst or that particles that would be forms that would be strongly bonded with the support materials that is used when it is prepared, and depending upon that the reactants will be converted. A specific nanomaterials and a specific products may forms depending upon that materials we have prepared. Okay. So, now first one examples we will discuss about the nanoparticles size effect on binding energy of adsorbents. So, when the reactants we considered, so whatever the reactants, that may be any hydrocarbons or any compounds that may be reactants that come in over the surface of that nanomaterials and active sites are present, there it get adsorbs. Okay. So, then adsorptions, when it is adsorbed, so there is some bond strength of that adsorbate with the surface that is present, and after that so the molecules may converted into desired products. Okay. So, now the relative thermodynamic stability of those reactants or reactant intermediate over the surface, that is very crucial. So, how this the strength of the molecules particles bonds depend on the size of the supported metals nanoparticles, supported metal nanoparticles that we will discuss. So, here's examples. One will show that CO carbon monoxide, the adsorption energy on particle size and different supported model system that we will discuss particularly here. Palladiums, that is the materials that would be deposited a particular surface or supports we can say. So, there is this palladium that is in terms of nano. So, its size we will vary 1.8 or approximate 2 nanometer to 8 nanometer. So, within that range we will check these nanomaterials that will prepare, and then the adjustment reactions theirs will discuss. So, it has been observed that initial heat of adsorption of CO2 molecules when particle size was 8 nanometer palladium particles, it was observed that 126 kJ per moles means CO2 molecules get adsorbed over that palladium particle, and particle size of the palladium that was 8 nanometers. When that particles of palladium particles that is converted into 1.8 nanometer cluster. So, here the adsorption energy CO2 molecules that would get adsorption energy is decreased. So, 126 to 106. So, here you can see the different particle size. So, this is 8 nanometer particles, this is 4 nanometer particles, and this is approximate 2 nanometers of that palladium nanomaterial that was prepared for CO2 adsorption study. So, here's heat of adsorption. You can see heat of adsorption when that material was 8 nanometers. So, then it was close to 126 kJ, and when it is gradually decrease the particle size or palladium size. So, then the adsorption energy of CO2 in that particular surface of catalyst that is decreased. So, after that we have this we will discuss about CO2 conversions. So, here you can see bulk gold particles. If we are able to prepare bulk gold particles, so it has been observed that bulk gold that is inactive, many chemically inactive for this particular transformations of CO into CO2 that does not react. When this gold converted into nano size that is less than 5 nanometers, you can see. So, that is very effective at low temperature for CO oxidation. So, here's CO oxidation activity that was studied by changing the gold nanomaterials particle size. So, here the gold metal oxide that was highly effective when it is in that range. So, very small particle size less than 5 nanometers, but when it is bulks or more than 8 or 10 nanometers, so then that does not react or does not convert CO into CO2. So, inerts. So, here also you can see the particle size of the nanomaterials. So, turnover frequency also for this particular reactions you can see the turnover frequency that was expressed in terms of y axis and in particle size of that gold nano gold that was prepared. So, here when it is 1 to 2 3 nanometers, 4 to 6 nanometers, and then 3. So, when it was 3 nanometers gold oxide that was deposited in a particular support. So, here that materials gold is turnover frequency was highest turnover frequency or for this particular particle size of gold that was much more effective. So, another examples we will discuss about the Fischer-Tropsch synthesis, that is the reactant is syngas and that would be converted into hydrocarbons fuels. Here also particle size that is cobalt catalyst that can be used for this particular reaction. So, here if you are able to prepare cobalt nanoparticles, that is very effective, and that particle size of the cobalt that is also very crucial. So, it has been observed that the cobalt that particle size if we go from 2.6 nanometer to 6 nanometers from here to this, you can see the catalytic activity gradually increase. So, cobalt particle size if we grow from 2.6 to 6 nanometers, within that activity increase, and further if you increase the particle size, so then catalytic activity gradually decrease. So, this would be the optimum range within that. So, that particular cobalt nanomaterials or nanoparticles that you have to prepare, and that is specific for this particular reactions to get higher yield, higher conversions. So, that is very crucial to prepare the nanomaterials or nano size particles for the specific applications. So, what would be the particle size? So, another example We can see here iron oxides Fe3O4 ferrosulfuric oxides that we can use for this carbon monoxide to CO2 conversion at this temperature 450 kelvins. The reactions can be occurred. So here metals and strong metal support interactions is also very important, since the materials irons oxides Fe3O4 that was distributed, let us say, any support materials. So here's iron oxide ferrosulfuric oxide that is distributed over the supports and forms a very small particles. Okay, so here's that can be used. So here's iron platinums that was the catalyst that was calcined at 850 degrees centigrade and 600 kelvins and 850 kelvins. So here's Fe3O4 that is also active. So CO2 conversion CO2 productions that was follow like this way. When the same materials that was calcined or annealed at 600 kelvins, the CO2 production slightly increased. When the same materials calcined or means calcined at high temperature or annealed at high temperatures, the CO2 productions gradually increase. So here's means the conversion such kind of phenomena means why the increasing higher calcination temperatures. So metals, actually the platinum that is the active sites, so that is encapsulated with iron oxide ferrous FeO ferrous oxide. So that actually enhance the catalytic activity or conversions of CO2. So high calcined temperature, so there is a strong metal support interactions means Fe2O3 and platinum. So that platinum is encapsulated with iron oxide, so then we can get a good activity or higher conversions or activity. So here another examples I am showing. So the nanomaterials size means for propene epoxidation reactions, here propenes that would be used for epoxide propene oxide formation, epoxidation of propenes. So here gold particles was used, gold particles 1 to 2 nanometer, 2 to 5 nanometers, more than 5 nanometers. So that gold particle size. So here support was taken titania. So gold titania, that materials was prepared by impregnations method or co-precipitations methods we can prepare. So it has been observed that so when impregnated by this catalyst or gold was impregnated over titania, so only CO2 was observed, means propene epoxidations in presence of oxygen or hydrogen. So CO2 is the product that forms. So when gold titanium was prepared by co-precipitation methods, so only propylene oxides that was observed. So now the particle size of gold, so if you are able to prepare less than 2 nanometers within that range, so then propane formations is there. So propene would be converted into propenes. So propene formations is there. So here only one product, that is propenes, we can get. And whence the particle size 2 to 5 nanometers, so there propene oxide formations is there, 2 to 5 nanometer propene oxide formations is there. Propene is converted into propene epoxide formations is there, that was observed. So then titania silica both supports were used. So when only titania was used, so then the product yield was low. When titania silica and particle size was 2 to 5 nanometers, so then yield was slightly increased. So when particle size was more than 5 nanometers, so here you can see, so only water formations is there, CO2 formations is there. So instead of desired product, undesired product formations is there. So then particle size, so if you want to get propylene oxide, so then particles method of preparations is important. At the same times particle size 2 to 5 nanometers within that range is very crucial to prepare a catalyst or disperse that gold nanoparticles upon the surface. As a result, we can get the good amount of yield of that desired product. So that is very crucial. So here different type of titania silica support was used, and that was gold particles that was dispersed over that supports, and then that was used for propene epoxidations. Here also epoxidation. So depending upon that, the conversions will vary depending upon that support materials that was used. So I said only titania silica can be used. So titania silica is much more better, give more product yield than individual titania. So product selectivity also change depending upon the type of support we have used. Okay, so here also you can see concentrations of the gold, that solutions that we use for preparations of the gold nanoparticles that would be dispersed in a specific support, that may be titania silica or mixed titania silica composite or MCM41s, any supports we can choose, and there we can prepare. So concentrations is very important. Depending upon that, the conversions of proteins, that will be changes, as well as propene oxide selectivity, that also will vary. So now here I said titania, graphenes or graphene oxide. So we can use it as a carbon based nanomaterials. So that would be means combines with that TiO2. That TiO2 also another type of metal oxide photocatalytic activity is there. This type of the material. So that can be used for photocatalyte as a photocatalyst for different type of contaminants that is present in water, so that can be degraded. So here's so many advantages are there. So by using titania as a photocatalyst, so with that graphene oxides also we can use, since graphene oxide or graphenes, so that we can use with titania. So in individual titania we can use, and or graphene titania graphene oxides, that would gives better performance than only titania. So this graphene or graphene oxide, actually that is with titania composite we can prepare. So actually the titania acids, there are two different phases, rutile and anatase phase. And graphene oxide, when it is, or graphene sheet forms composite materials, it enhance the photocatalytic activity. So we can use titania as a photocatalyst, and with that, with carbons means graphene or graphene oxides, with titania we can make a composite materials that also can be used for the photocatalytic reactions. And when we are using this type of carbon based nanomaterials with titania make composite materials, that would enhance the photocatalytic activity. Actually this type of materials having high surface area also very, actually the conductions of electrons. So whatever when photocatalytic reactions is there, so there are various type of peroxide, oxide, hydroxyls, radicals, species formations is there in photocatalytic reactions. Then those, actually this graphene or graphene oxides, so assist in stability of this type of radicals, so that actually assist in degradations of bio base or any pollutant that is present in waters. So here's actually you can see, so titania, when light is fallen over there, so then electrons and hole formations is there, hole and electrons, that is valence band, conductions band. So then whatever the hole is present, so an electrons is also present, so that is formed. So when light is falls, UV lights that is fall on titania. So then waters or oxygen, these are the molecules are present in water, so that would be interact with these hole or electrons and then form OH radicals or peroxide radicals. So these are the actually key components that directly interact with that pollutants, organic pollutants are present. So these interact and degrades that organic pollutants. So here's that way we can degrade that catalytic reactions by degrading the using this photocatalyst or different type of graphene oxide nanomaterials, we can degrade those organic pollutants that is actually present in wastewaters. Okay, actually these roles of this graphene or graphene oxide, how this graphene oxide actually enhance that photocatalytic activity. Actually when those are the radical formations is there, increase the photogenerated electron affinity holes lifetime. So actually these graphene oxides actually enhance that lifetimes of those holes and electrons are formed during photocatalytic activities. Okay, and therefore the degradation efficiency or performance will increase. Okay, so here different quantity of graphenes was used for preparation of this composite, titania graphene composite. So here it has been observed that, so 2%, 4%, 6%, 8%, 10%, different weight percent of graphene was used to prepare titania graphene composite. So 6 weight percent was the optimums. So that would gives better results in terms of conversions of that organic pollutant present in wastewaters. Okay. So how this graphene oxide, I said already, the increase the stability of those holes and radicals that is forms, that this graphene oxide act as electron sinks for that photogenerated electron that is forms during photocatalytic activity. So these are the means, also it enhance the surface area of the titania, means graphene or graphene oxide having exceptionally means very good or high surface area. So when we use those materials with titanium, make a composite material, the surface area increase, as a result that also increase the performance photocatalytic activity. Also this graphene oxide enhance that adsorptions of that contaminant that is present in wastewater, that adsorbs, assist in adsorptions and enhance that photocatalytic activity. Okay. So, apart from that, so there are some electrocatalytic conversions, photocatalytic conversions also for CO2, means we can use different type of nanomaterial, and that can convert those CO2 into different value added products. So, by electrocatalytic or photocatalytic reactions. So, here's a various type of nanomaterials already we have discussed. So, metal based metal oxide, bimetals, monometal, trimetals, or different type of metal oxides we can use, and different preparations methods are also there, so that we can use for conversions of CO2 into value added products. So, here gold, palladium nanomaterials, copper, MOF, nickel MOF. For CO2 reductions we can use rhodium, silver nanocatalyst. For CO2 to formic acid or acid productions we can use gold, titania, graphitic carbon nitride, that can be used for that also, means water and CO2 into CO and methanes value added products formations. Gold CDS, that also can be used for artificial photosynthesis reactions, and there's so many other materials also is available. So, different materials are available that can be used for a specific reaction, that in terms of thermocatalytic or photocatalytic. So, depending upon that specific reactions, so that materials we can prepare and we can apply for that particular reactions. So, here electrocatalytic conversions, so CO2 that can be converted into different valuable products by electrocatalytic conversions, and there we can use nanomaterials that is useful for this specific conversions, formic acid, formaldehyde or methanol formations. So, here I am not going to discuss more details about the different materials. So, here porous nanomaterials we can use, noble platinums we can, non-noble metals also we can use, bimetallic catalyst also we can use. So, that is in the form of nano range. So, 1 to 10 100 nanometers within that range. So, that may be specific metals that is useful for specific reactions. So, that can be used. Okay. So, here's different photolite reactions also is there. So, photocatalytic reactions. So, I am not going to discuss more details on this. So, here's another one is the core cell nanoparticles. So, that is also can be synthesized by using core cell methods. So, the nanomaterials or nanoparticles that can be prepared by core cell methods, and that can be used for specific reactions as a catalyst. So, different core cells nanoparticle synthesis methods are available. So, and that can be used for various oxidations, reductions or coupling reactions that can be used. So, here in core cell methods, the core cell nanoparticles that can be classified based on their compositions used or preparations methods, and based on surface property, these core cell nanomaterials we can classify into hollow core cell nanoparticles, core multicells or core porous cells nanoparticles that we can classify, or core cell nanoparticles that organic based or inorganic based, that we also we can classify, or inorganic based, silica based or metal based nanoparticles we can classify. If it is silica based, then silica gels or template assisted methods that we can prepare core cell nanoparticle, or if it is metal based, then metals, metal oxides or other metal salts, halides or chalcogenides we can use. Depending upon that, a specific core cell nanoparticles or nanomaterials we can prepare, and that can be used for various reactions. So, whenever we prepare those materials, so the performance of these core cell nanoparticles that depends on that shape, size, surface charges, surface area compositions, that is we prepare size distribution, structure, concentration and agglomerations. So, many means there this nanocatalyst property that depends on different means properties of that nanomaterials we have prepared. So, okay. So, here one or two few examples we will discuss about liquid phase heterogeneous reactions, that is there we can use core cell nanocatalysts. So, nanoparticles that may be different metal or metal oxides that would be distributed. So, here one or two examples we will discuss here: palladium and nanoparticles, that is course prepared by core cell method. So, here glucose was used as a carbon's microspheres. So, that blue colors you can see, that is glucose that having different functional groups, and then palladium's precursor was distributed. So, then carbospheres palladiums, and then in the step 3 ceria was impregnated by hydrothermal methods, and then carbosphere palladium ceria that species forms, and then we can calcine that. So, then these carbons we can remove by calcinations. So, then here you can see the palladium ceria. So, means palladiums that is distributed in the form of nanomaterials, and ceria that's actually coated outside of that ceria, palladium nanoparticles. So, its structures you can say like this. So, inside whatever that glucose materials, the carbons microspheres that was present, that was removed with the help of oxidations, means calcinations in presence of air. So, we can prepare this type of materials. Also, there are some other materials also, porous silica, gold silica. These materials also we can prepare, means in that core silica is present, first amine functionalizations was there, and after that gold was distributed in against silica was distributed. So, after that in presence of base sodium hydroxide we can remove those silica. So, after that it can produce porous material, that is silica, gold silica, this type of materials. It's this type of materials actually gold particle dimensions is very small and nano range. So, this type of material is very effective for epoxidations of styrene. So, here you can see this is the reactants and this is the products. So, it can be converted by using this type of nanomaterials for epoxidation reactions actually. So, here using this type of catalyst, so the conversions is very high as compared to the conventional catalyst. So, similarly some other reactions is also, means here's nitrates we have taken silver nanoparticles with ceria, that catalyst can be used for hydrogenations, means here's reductions reactions nitrate to amine formations. So, here also this catalyst nano catalyst by core cell methods we can use silica, palladium, zirconia, that also can be prepared similarly, means core cells methods, and that can be used for different type of reactions. Here this is the substrate and this is the products. So, for this particular conversions we can use this type of silica, palladium, zirconia, this catalyst. That catalyst is very useful and giving very good conversions and very good selectivity as well as product selectivity. So, here's another example is palladium silica TIMS core cells methods. Here's support is titania containing mesoporous silica cells that was used, and that materials was prepared by different way. So, this is very effective for this type of reactant to convert into this type of methyl phenyl sulfide into sulfoxide preparation. So, in this oxidations reactions. So, here actually this palladiums, role of palladiums to convert hydrogen and oxygen that is present in peroxide, that is actually oxidized this sulfur that is present in that particular methyl phenyl sulfides to convert into oxidations. Okay. Similarly, other reactions is also there. So, here's this alcohols to ketone formations, here's this catalyst can be used, here's means the catalyst that was prepared core cell methods, the catalyst that is prepared. So, here step by step method is given. So, here's double layer hydroxide formations is there, magnesium, aluminum double layer hydroxides, that is very effective for this particular oxidations of alcohols into ketones compounds. And here is gold nanoparticles in silica. So, that also prepared by a core cell method. So, here's without gold and this is with gold, so means gold nanoparticles. So, both can be used for this particular reactions. So, here is also very effective this particular catalyst. So, here another means iron oxides in silica nanoparticles that can be used for ammonia decompositions. Here's the materials was prepared by silica that was coated by core cell methods over oxides, and these materials was prepared that can be used for ammonia decomposition at high temperature, that is very stable at these temperatures, and this type of iron nitrates species formations is there or phase formation is there during reactions. So, these are the method, means different type of nanomaterials that can be prepared by core cell method, that also we have discussed today up to this. So, through this study we have discussed a different type of nanomaterials that can be used for different type of catalytic reactions, that size effect and preparations method also very important to distribute that nanomaterials in the nanoforms, and that specific size is very important. So, for specific reactions to get a good conversions as well as good yield. So, today is up to this. Thank you.